So we're still investigating things about the electron. So remember we said that light, we have particles and we know that it's going to act like a wave and we know it's going to act like a particle. And that's for light. But we wanted to also associate that concept with my electron. So my electron can absorb energy, can release energy, and we also know that it's going to be in different, it's outside the nucleus, and it's going to be moving around outside the nucleus. Okay, and we'll talk about where specifically it's at in a little bit. But if it's moving around outside the nucleus, and it is matter, then how can I talk about how much energy that has, that electron, related to how much it's moving, how fast it's moving, and its size? So in 1924, a French physicist named Louis de Broglie theorized that if light can have material properties, then matter should exhibit these wave properties. So everything that we've talked about with light, we can also apply to the electron. That's pretty much what he was saying. We can apply to our matter. And so what he predicted is that the wavelength of a particle is related to how fast it's going, its momentum. And so from all of that, he was able to figure out an equation. And this is his de Broglie equation. So my wavelength is equal to h over mv. So h here is my Planck's constant. And remember, Planck's constant is joules times a second. M here is my mass, and my mass has to be in units of kilograms. And my v here is my velocity, or my speed, and that's in meters per second. Now you might be saying, well, why is my mass in kilograms or whatever? So remember when we talked about joules, we said joules was a subunit. So remember the subunit of a joule had a kilogram and had meters and had seconds in it, kilogram, meter squared per second squared, all of that. So since the joule has kilograms as its mass subunit, we have to match it, okay? Or just kind of remember that de Broglie uses kilograms, whatever works. So here, I'm relating my wavelength to Planck's constant, the mass, and the velocity. So I've noticed that the wavelength is inversely proportional to the velocity, okay? So as one goes up, the other goes down. Now, because the mass of an electron is so small, remember the mass of my electron is really, really small. So this number is going to be a really small amount. This means that the wave character, because this number is really small, that means this is going to be really big, my wave character is going to be very significant. So because I'm talking about a very small in mass particle, then its wave nature is going to matter. So it's going to matter enough that I need to take this stuff into consideration. Okay? So the wavelength is going to be affected by the velocity, how fast I'm going. So let's look at a problem. What is the wavelength in nanometers of an electron moving with a speed of 5.97 times 10 to the 6 meters per second? The mass of an electron is 9.11 times 10 to the negative 28 grams. So we got a lot going on. So let's just say, what am I looking for? So I'm looking for the wavelength in nanometers. And at this point, there's lots of ways I can find the wavelength. I know C is equal to lambda V. I've got my equation, my E equals hc over lambda equation. I've got my Rydberg equation. And now I have my de Broglie equation. So I've got lots of ways that I can find lambda. So which one of these multiple equations I'm going to use depends on what they give me. So this next part is really important. What was I given in the problem? So I see this number. This number represents the speed. So the speed is going to be 5.97 times 10 to the 6 meters per second. Now, this is speed, not frequency. Okay, so it might even be helpful for you to write speed here, anything of that. Excuse me. So don't let this get confused with frequency that we talked about before in our C is equal to lambda V. That V is frequency, not speed. And they also give me the mass. So the mass is 9.11 times 10 to the negative 28 grams. So de Broglie should really stand out because de Broglie's the only guy that has speed and he has mass in it. So if I'm talking about the mass and the speed, then that kind of gives me a hint that it's going to be the de Broglie equation. Because my C equals lambda V has frequency, not speed. My other equation has energy in it. I don't have energy. Then my Rydberg has ends. So this is de Broglie's the only guy that has speed and mass. So I need to write down my de Broglie equation. So de Broglie was lambda is equal to H over mv. All right? So let's think about, do I have, I'm looking for lambda. H is a constant, okay, so I have that. H is just 6.63 times 10 to the negative 34 joules times a second, so I'm good there. Mass, I have the mass, but before I plug it in, is it in the right units? So remember we said that the mass needs to be in kilograms, but they gave me the mass in grams, so I want to convert that. So if I'm trying to go from grams to kilograms, I need the grams to cancel. Grams go on the bottom, kilograms go on top. Kilo stands for 10 to the third, so it goes on the opposite side of the prefix, so it goes on the bottom. I do that math, and I get that it is 9.11 times 10 to the negative 31 kilograms. All right, and then the next thing is the speed, and the speed was just simply in meters per second. And my speed or velocity is in meters per second, so we're good. So now I have all the parts in the right units, so I can plug it in. So lambda is equal to H, 6.63 times 10 to the negative 34 joules times a second. Mass was 9.11 times 10 to the negative 31 kilograms. And my speed is 5.97 times 10 to the 6 meters per second. All right, so do all the math. This guy divided by this guy, and you end up with 1.219 times 10 to the negative 10. And your question might be, well, what are the units? Now this one's a little trickier for us to see because the joule has subunits. Okay? So remember the joule had the subunits of a kilogram, meter squared per second squared. Okay? So if it has subunits, I gotta try to figure it out. So let's try to figure out the units. So a joule was a kilogram, meter squared per second squared. And this is times a second. And that's all divided by a kilogram times a meter per second. So I just wrote out what the joule was, times a second, and then the kilogram meter per second. So here the kilograms cancel. Here, one of my seconds are going to cancel. Kilograms cancel. One of these seconds are going to cancel with this one. So it's going to be 1 over a second. So here would be 1 over a second. Here's 1 over a second. So all the seconds end up canceling. And then you have a meter squared on top and a meter on the bottom. So when the meter squared on top cancels with the meter, all you have left is a meter. If you're completely lost by all of that, then all you can remember is that this wavelength is in meters. Okay? That's one easy way to remember. Same as the Rydberg. The Rydberg was in meters, this guy's in meters. Okay? So then I said, okay, cool. I got my wavelength, he's in meters, but I wanted him in nanometers. This is going to be really common. Pretty much always want it in nanometers. So let's do that conversion. So 1.219 times 10 to the negative 10 meters. I don't want meters. I want nanometers. So meters go on the bottom, nano on top. Nano stands for 10 to the negative 9, so it goes on the opposite side. Meters cancel, and I get 0.122 nanometers. Okay? Now, with these problems, it doesn't really tell me much about the electron other than its speed and its mass. So it's hard for me to know in what part of the spectrum is my wavelength. Okay? So it's hard for me to know, is that a right answer or not? Okay? So as long as you don't have something that's like 10 to the negative like a really big negative number, like negative like 7 or up to like 40, then you're fine. So as long as it's still, you know, kind of a decent number, not too far below 1 or bigger, then we're okay. All right? So this was our relating the speed and the momentum of our electron to the wavelength. So now we've kind of tied it all together. But the last thing we need to talk about is exactly where are my electrons. So now we kind of know how the electron's going to behave. It's going to be similar to light. So he's going to act like a wave. He's going to act like a particle. We know that he can only move up on those staircases or down on those staircases. We know that energy difference and how it's going to be moving and its wavelength is related to its mass and to its speed. But now we want to say, we know that the electrons are outside of the nucleus. They're somewhere in the empty space outside, but where? And so the last part of this chapter is probably the most important part of this chapter because it's going to carry over into the next part, okay, into the next chapter in chapter 2. So this part we're going to start, or chapter 3, sorry. So now we're going to start talking about where are the electrons exactly when they're outside the atom.